Hello, for all you statisticians out there in quarantine land or absent today, I just wanted to give you a real quick walkthrough of the notes. So stay with me, and this is something you can fill in from the notes packet key. And let me know if you have any questions, okay? So to start off with today, we're going to be talking about center, which is one of our SOCs. And we have two ways that we tend to talk about center, which are mean and median. And sometimes we talk about mode. But a lot of times we'll leave mode for, say, categorical data, where we say the most frequent category or the least frequent category. When we're talking about numerical data, we almost always use mean, which is the arithmetic average. That's the add them all up and divide by how many there are number. Or we use median, which is that middle value of the data set, where we talked about that last time, about separating the data, cutting it in half, whatever that central value is. When we are talking about mean, there's a couple of notation things you need to add to your toolbox. And the first one is that mean, we can talk about that in two ways. We can use a sample or a population. Now, if we're talking about a sample, the symbol we use is an X with a little line over the top of it, and we say X bar. So if I write X bar, that means I know that this is an arithmetic mean, and it is from a sample set of data. And the other one we have is this kind of little fancy M, all right? So this is the, mu, which is the Greek letter that we will use for mean. So in general, in statistics, we have a tendency to use Greek letters for populations and English letters for samples. To compute a mean, it doesn't matter if you're talking about a sample or a population, you basically add them up and divide by how many there are. So if you see that sigma x, that means the sum of all of the observations. So you add them all up, divide by how many. Just another clarification, we typically use n, lowercase n, for sample size, and capital N for the number of observations in a population. Okay, so to kind of like everything versus the little piece we took. If we want to find the mean, for example, students were asked to estimate the incline angle of a ramp leading up to a loading dock. A sample of the responses is given below. Find the mean. Basically, again, you need to add them up and divide by how many there are. And I would suggest that you always show your work for this, which seems kind of frustrating because it's like, well, I could just do this in my calculator. I know that. I would recommend you always write the original sum divided by the number of observations, because that way if you do make a mistake, there's a great chance that you could get partial credit. Okay. The other thing is, since we are talking about incline angle of the ramp, I want to make sure that I put my unit on there. So no naked numbers. So this would be 53.6 degrees. Now, the other thing that you need to always be able to do is interpret the mean in context. If you're ever asked to do that, what does this mean? What does this mean? Interpret. A mean is a typical value of the variable. And so we would say something like, well, what were the students asked? They were asked to estimate the incline angle of the ramp. So 53.6 degrees is a typical value of the estimated incline angle of the ramp. Okay, so anytime I find the average, if I say that the test average was a 85, then I would say 85 is a typical score on the AP Stat exam. Okay, so a typical value of the variable, and you want to write that in context. Now, the other thing you need to be able to do is deal with a frequency distribution where you have several of one number. So, for example, it said students were asked to report the number of hours they spent studying for an upcoming test. They were allowed to choose 0, 1, 2, 3, or 4 or more. If they're 4 or more, we just put them in as 4 in the table. So I'm sorry, 5s and 6s and 7s and 8s, we're just going to count you as 4 for the sake of this problem. So remember, when this frequency tells you how many there are, so there is one student who answered 0, 3 students who answered 1, etc. So if I was to actually add these up and divide by how many, it's 0 plus 1 plus 1 plus 1, because there were 3 ones, plus 2 plus 2 plus 2 plus 2 plus 2, etc. 7 of those, 1, 3, and 1, 4. So what we really have are 0 times 1, there was 1 of those, and 3 1s, and 7 2s, and 1 3, and 1 4. So you can see how it's the hours spent times that frequency. So this many times. Now, if I do this, this gives me a sum of 24, but the catch is it's add them up and divide by how many there are. So you want to make sure you actually divide by how many there are. So there aren't 1, 2, 3, 4, 5 things. There are 5 categories. There are actually 13 values. So my sample size is actually the sum of the frequency. So that is 24 divided by 13, which is 1.846. Okay, now if I was going to do this in my TI Inspire, what I would do is I would say add a list and spreadsheet, and I would put in an X for my value and an F for frequency, and I'm going to type in these numbers 0, 1, 2, 3, 4, And then I'm going to go in and add those frequencies, 1, 3, 7, 1, and 1. Okay, and then I'm going to run my one variable statistics. So I'll say menu, statistics, stat calculations, one variable statistics. Again, just click through this one list. For my X list, I'm going to click down in this box and I'm going to choose X. That was where I made my variable. And what's different from what we did in the past is this frequency list here. I want to select F for frequency. So this tells me how many there are. Okay, so you'll notice that my average is 1.846, which is the same. So you see that X bar. We could also find standard deviation here. If this was a sample of students, we'd use the S for standard deviation, 0.987. If I wanted my 5-number summary, I've got that too. My minimum, Q1, median, Q3, and maximum. All those are there. Okay, all right, so here's another example, and it says the mean scores for the students in class by major are shown below. What is the mean score for the class? So 9 engineers had an average of 85, 5 math majors had an average of 90, and 13 business majors had an average of 81. So again, what we want to do is we know that the 9 had an average of 85. So if we did 9 times 85, that'll tell us how many actual points they had as a group. And then 5 times 90, and then 13 times 81. That's going to give me all my points. And I just need to be careful because if there are 9 of these and 5 of those and 13, instead of dividing by 3, I'm going to divide by 27. Okay, so again, I end up with 84 points. After you've done this, you want to stop and ask yourself, does this make sense? Would it make sense? I see 85s and 90s and 81s. Is 81 a reasonable average for this? And the reason why I say that is because people do have a tendency to do something like this. So they'll take their calculator and they'll type in 9 times 85 plus 5 times 90 plus 13 times 81. Okay. And hit enter, and then they'll see that there are 3 different classes. So instead of dividing by 27, which is how many students, they'll divide by 3, and you get 756. And I'm sorry, 756 is not a reasonable average for these numbers. So that should be a cue that you've done something wrong. Okay, so always going to stop and ask, does this make sense? Here's another one. It says fuel economy in miles per gallon for 30 small cars. In this case, they're given to us as a range. From 29 to 33, we had 11. And from 34 to 38, we had 12, etc. So if you're ever given a class, one of the little things that you can do to kind of estimate the mean, and you won't have it perfect, but to estimate it and give you a rough idea, is to use the median of the class. So I do 29 plus 33 divided by 2 and get 31. And I say, I've got 11 numbers that are on average about 31. Okay, so find that median of the class to use as your estimate. You'll see 11 and 12 and 2 and 5. That gives us our denominator here of 30. We get an estimate of 36.17. And again, that's miles per gallon due to the context of this problem. Okay, now, another kind of mean that we are sometimes interested in is one called the trimmed mean. A trimmed mean is one where basically if you want to think about it, you're going to drop off your lowest and highest scores and get an idea of what's going on in the middle. This is really good if you ever have outliers on the side and you think the outliers might be unnecessarily inflating your mean in one direction or the other. So what you will do is, if I was normally going to find this mean, it says you have the following test grades so far in AP statistics, etc. There are 10 of those, so I add them up. They add up to 814. I divide it by 10. I've got an average of 81.4 points. So I decide I'm going to offer you a deal, and I will give you a 10% trimmed mean. Now, to compute a trimmed mean, basically you take the sample size and you determine what 10% of that is, or 20%, or whatever your trim happens to be. So if I take 10% of 10 numbers, I get 1. Now, if this was like 1.1 or 2.8 or something, just round to the nearest counting number if you do that. What that means is if I get 1, I'm going to trim not just the highest, but the lowest 1 value. So I'm going to get rid of the 28 and the 105 because 28 was my smallest value and 105 was my largest value. So basically I said, hey, listen, I will drop your lowest score, but I'm also going to drop your highest score, and I'll give you the average of what's in the middle. Okay, so our new X bar then, we only have 8 values left. So I take 100 plus 92, I don't use the 28, 87, 89, etc. Those add up to 681. 681 divided by 8 is 85.12. So that is a higher mean because it excludes those values. Basically that 21 was, or that 28 was lowering your grade more than the 105 was bringing it up. Okay, now if I was going to take trim mean, I wanted 10% trim mean. I had 298 numbers. Again, I'm going to get 10% of 298 is 2.98. Okay, in which case I'm going to remove the 3%, the 30 on both sides. Okay, all right. Now, as far as comparing mean and median, here's something that we know is true. Okay, if you have a graph that is roughly symmetric, the mean, median, and mode are all almost in the same place. But when your distributions are skewed, that mean tends to be pulled in the direction of the tail. Sometimes we'll say that the mean follows the skew. So if you have a lot of low extreme values, the mean will be more on the left side of the graph than the median will be. And if you have a right skewed, the mean tends to be on the right side. All right, so for example, sample A here is 1, 2, 3, 4, and 5. The mean would be 3, add them up, divide by how many there are, and the median is also 3. And since those are about the same, then if I was looking at this and I was trying to make a guess of what the shape is, I would guess the shape to be approximately symmetric. Now, without the actual data, I can't know that for sure, so remember that we're just making a guess. On the other side here, I've got 1, 2, 3, 4, and 500. Okay, so wow, that's a big number. I add those up and divide by 5. I get a mean of 102 and a median of 3. So I would guess that since the mean is to the right of the median on a number line, that this would be data that would show a right skew because the mean follows the skew. Okay. Now again, I am just taking a guess, but that's kind of how we would look at this. Also notice how much that big number, which is going to probably be an outlier here, right? This outlier right here has a dramatic effect on the mean, but it doesn't affect the median at all. Okay, so what we have noticed is that there are some kinds of values that are what we would call resistant statistics. They're not affected by extreme values. So if you've got an extremely large or an extremely small value in the data set, it doesn't tend to pull towards that value. Resistant statistics would be things like median. The median doesn't really care what's happening on the edges. It only happens on what's in the center. And so if you have a really high outlier, your median is still going to be a nice measure of central tendency there. IQR is another one that's mostly resistant, even though it is a range, because if you're talking about extreme values on the end, the interquartile range is that middle 50%. So 1 or 2 high extreme values are not going to change that range in the center. Non-resistant statistics, or ones that don't do a good job of hanging on to their position once you've entered in a really high or a really low value, are things like mean. And you know this is true. If you were to have a whole bunch of 90% on a test, and then all of a sudden you come in and you get a 28, your mean's going to go whoop way far down. Okay, same thing with range. If you have a really high outlier and you get rid of that high outlier or you put one in, that's going to have a dramatic change on the overall spread of the graph. And standard deviation is another one that is non-resistant, which we're going to talk about here in our very shortly. Okay. All right, so when we're talking about mean versus median, here's the idea, okay? We like the mean. Mean is the best one for us because it uses all the values and it's algebraically defined. We like the mean because it is algebraically defined, okay? There's a formula for it. It can be programmed into a computer. We like it because every single value is included. So it is definitely using every single value. I don't like it because it's very distorted by outliers and it's distorted by skewness. As far as the median goes, it's not distorted by outliers or skewness, which is good, but it ignores most of the middle information, everything except for the middle information. So all the information is not being included. There are literally only 2 values needed to consider where that median is. Also, there's no algebraic formula for the median. It's more of a process. You put the data in order, you find the central value. If there's no center value, you find the mean of the 2 center values. There's no add them all up, divide by how many there are equation for it. So it's not really for us, if possible. So when we're talking about distributions then, we're getting to that center. How do you decide which center to use? So here's your general guideline. We talk about SOCs because we're going to start with shape. Always start with the shape. If you go to talk to the shape and the shape says, hey, I'm skewed, or hey, I'm symmetrical, that's going to guide you in the right direction for center and spread. So if you have a skewed distribution, Or if you have one that has outliers, like really obvious, really large or small outliers, the median is the best measure of center to use. Okay, so if you have a very skewed distribution or you have extreme values, you're going to want to use median as your measure of center. That is going to be the best judgment calls for a typical value of the variable. Okay, if you were to have a whole bunch of 90s on a test, and then all of a sudden you have one, you have a bad day and you get a 28. That's going to lower your arithmetic average quite a bit. We've got that outlier in there. But if I was going to say, what's a typical performance that you have? Your performance is around the 90s. So that median is going to be a better indicator of that. Now, if you have symmetric distributions or approximately symmetrics or ones that aren't real skewed, they may be just slightly skewed, then we really want to use mean, because mean is a better overall measure of center because it does include all of those data values. Okay, so when we're talking about center, start with shape. If you see a large skew or you see extreme values, go with median. And if you see something that is approximately symmetric, you want to go with mean. Now, the other part of this would be is if you're dealing with a box plot, like if they give you a box plot, no matter if it's skewed or symmetric, you're going to talk about median because median is right down the middle of that box, already there for you. All right, so the next video will be about standard deviation. I'm going to pause and we'll come back in a few.